Before we can understand the dynamics of an aircraft, we need to step back and just understand some fundamentals of dynamics in general. Okay, so hopefully this is a review for you. Hopefully you've had some exposure to dynamics before, but we're going to work through just a really simple problem here of a spring mass damper system. Okay, so this is a very common problem that they look at in dynamics because it teaches us so much about a system. So we're going to look at some mass here and say that that's connected to some ground location by a spring of constant K, and there can be some force on this mass. We call this a forcing function, so something can be pushing and pulling on that mass. And finally, the last thing we need to add here is what's called a damper. So this damper is something that's also fixed in place, so to speak, but this is going to have a strength of C, and that provides a force in the opposite direction of the motion of the mass. Okay, so it's like a damper would be like friction, for example. It's always working in the opposite direction of the motion of the object. Okay, and then we're going to just define x in this direction here, and we're going to say that if this mass were at rest and if there was no forcing function, so if the forcing function were 0 and this mass was at rest, then it would be sitting at x equals x naught. Okay, and that would be at rest. Okay, but what if this mass gets perturbed away from this x naught location? Well, then there would be different forces that would start to act on this. And so let's look at all of those forces. So first of all, let's say that we could have a non-zero forcing function pushing us to the right, positive to the right, I guess I should say. So the forcing function could be positive or negative, but we're going to define it positive to the right. So let's just add up all of the forces on this mass now. If it gets perturbed from this equilibrium position, and look at those with positive being to the right. So first we'd have some spring constant K, so the spring would start to act on this, and it would actually if the mass was positive to the right, so if x was greater than x naught, then we would get a force to the left direction because that spring would try to pull it back towards the wall. So what we would get is a force on it that's it would be actually I want to put it'd be our constant K times delta x. Okay, so if delta x is positive to the right, then we'd get a force to the left that's negative. And of course, if delta x were negative, then that would give us a force to the right because that spring would be in compression. Okay, another force we would get on this mass is that we would get something proportional to its velocity. So something, it's going to be our C, our damping coefficient, that's proportional to the velocity of that mass, which is delta x dot. Okay, so the change in x with time. And if that mass were moving to the right, so if delta x dot were positive, we'd get a negative force on that because the velocity, or the damping is always opposing the direction of the velocity, so we get a negative out front there. And then finally, the last force that we're going to include on here is the force due to acceleration. So if that mass were moving, then it would have some acceleration with it as well. And so what we'd get there is mass times acceleration, which is a delta x double dot. So the second derivative with respect to time. And if that mass were accelerating to the right, then we would get a force in the left direction, and so that would be negative there. Okay, so all of these have to sum to be equal to 0 for to complete this equation here, to include all these forces on it. Okay, so let's just rearrange this now. We're actually going to move all of these terms to the left, or excuse me, we're going to move all of the negative terms to the opposite side of the forcing function. So I'm actually going to put the forcing function here on the right, and say that that is equal to, and I'm going to rearrange these to m times delta x double dot plus c times delta x dot plus k times delta x. Okay, so that's my, this is called a second order differential equation. Second order differential equation. Okay, so what we want to do now is kind of interrogate this equation to learn about the dynamics of this system, to understand how this mass is going to move if it gets perturbed away from its equilibrium point. Okay, and for most of for the rest of this course, really, we're just going to look at solutions where the forcing function is equal to 0. So the forcing function would be some external force on this, but we're just going to look at the natural response of this system. And so if this is true, that the forcing function is 0 on this, and we're just looking at the natural response if this mass were to get perturbed from its equilibrium position, then this is what we call the homogeneous solution. Okay, so homogeneous solution. And we could look at other solutions where that forcing function is non-zero, but that's beyond the scope of the current class. Okay, so we're just going to look at the homogeneous solution where that forcing function is equal to 0. Okay, so you might recognize the second order differential equation from another math class, but basically this is a very common equation where we have y double dot plus b times y dot plus c times y equals 0. This is a classic second order differential equation where we have three coefficients that are being multiplied by the second derivative of y, the first derivative, and y itself, and the summation of all of this has to be equal to 0. Okay, so the only known solutions to this problem are functions functions for y that can be written like this, where we have some constant times e to the, I'm going to call it lambda t. Okay, so this is an exponential function. These are really nice, as we're going to see here, because when we take the derivative of y, if it's an exponential function like this, we get something that looks almost identical, just with a lambda down in front here. So, for example, y dot is equal to lambda times c1, and c1 is just some arbitrary constant that would be set by the initial conditions here, times e to the lambda t. Okay, so that's y dot, and y double dot is equal to lambda squared c1 e to the lambda t. Okay, so all of these functions look really similar. They just have something different out front. And so when we plug these in now to this general solution, so if we take and plug these into this second order differential equation, what we would get is, once we plug that in, we're going to get a times lambda squared c1 e to the lambda t plus b times lambda c1 e to the lambda t plus c times c1 e to the lambda t equals 0. And we can actually rearrange this. All of these have a c1 e to the lambda t in them, so I'm going to pull that out front. So we've got c1 e to the lambda t out front, and what we're left with is a times lambda squared plus b times lambda plus c equals 0. Okay, so this term out front here, we could divide that to the right-hand side if we knew that it was non-zero. And so we're going to do that and assume that in order for us to solve this equation, we've got to have the internals here inside of these parentheses. That has to be equal to 0. Well, it turns out that that is simply the quadratic equation. So a times lambda squared plus b lambda plus c equals 0. That's just a quadratic equation, and we can use the quadratic formula solve that. And so the solution to that is that lambda is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so that's our solution there. Okay, so let's see how this applies back to our original problem now. So we have this. This is our original equation here. We recognize that it was identical to this form here, so we actually have solved this equation. But let's solve, or let's just plug back in now what our actual coefficients are up here. So instead of capital A, actually, a y double dot, we've got an m times delta x double dot. So we're using delta x as our y here. And so this first coefficient is just m. So I can plug in an m every place that I have an a here. So we'd have, for example, 2m. What's b up there? B is little c. So we're going to get minus little c plus or minus the square root of little c squared minus 4 times a, which is little m. And then the c here is little k. Okay. So that's what we get for these lambda values. Now, as you can see, lambda is it could be real or imaginary, depending on how the damping here, c, is related to the mass and the spring constant, right? So the things underneath this radical here tell us whether or not this is going to be a real number that comes out of this, or if we get an imaginary number out of this. But in any case, we're always going to get actually two values out of this. We're going to get a lambda 1 and a lambda 2, okay? We can get two solutions because we have the plus or minus here. So there's three different kind of characteristic things that could come out of this. So let's look at what those would be. So this lambda 1 and lambda 2, these are what are called our eigenvalues. And the eigenvalues, and for our case, we've got a lambda 1 and a lambda 2. These eigenvalues tell us about the dynamics of the system, what the dynamics are going to be like. Okay, if those eigenvalues are real, negative, and distinct, then we're going to get something that's called an overdamped motion. Okay, overdamped motion. If we plot that over here, so let's say that this right here is our equilibrium state along this axis down here, and if we get perturbed, overdamped motion says that I'm going to return back to my equilibrium state in a very controlled fashion, kind of this exponential move back to my equilibrium state. Okay, so that's overdamped. So if the eigenvalues are complex, I'm going to get something called underdamped motion. Underdamped, and what that means is that I'm actually going to, as I try to come back to equilibrium, I'm going to overshoot it, and then come back and overshoot, and if the real part of this is negative, I'll eventually dampen out. Okay, so that's called underdamped, and then finally, if these numbers are real, negative, and identical, I'm going to get what's called critically damped motion. Okay, and critically damped is an important case because it's the quickest path to return back to the equilibrium position without overshooting it. Okay, so it's kind of a a barrier or a dividing line between being overdamped and underdamped. It's the quickest way I could return back to equilibrium without overshooting. Okay, so let's talk just a little bit more. Well, first of all, we could use this information now to look at the ratio, between the damping C and the mass and the spring constant here, and come up with scenarios where we could say, well, it's going to be overdamped. For example, if C is much greater than these two, or if C squared is greater than this, then I'm going to get a real number out of this, right, out of the square root sign. It'll be negative and distinct if C is large enough, and then that'll be overdamped. Now, if C squared is smaller than 4mk, then I'm going to be underdamped. I'm going to get a negative under this radical, and so that will be a complex number. And then if C squared is equal to 4mk, then I'm going to get a real negative and identical eigenvalues. Okay, so we can just see that by looking at these equation here, what the ratio of the damping C has to be to the mass and also the spring constant K. Okay, so now there's a couple interesting things that we can learn from these eigenvalues. So for example, the damped natural frequency, if we have an underdamped system, then the damped natural frequency, omega d, is equal to the absolute value of the imaginary portion of lambda. Okay, so that is called the damped natural frequency. And that is the frequency that this will oscillate at, right? So we can predict the frequency based off of the imaginary portion of that complex number. Now, whether it's complex or not, we can compute what's called a damping rate. We use sigma for that, and that's equal to minus the real part of lambda. That's called the damping rate. Okay, and then no matter if these are real or imaginary, we always these eigenvalues always come out as a pair, because that we always have two eigenvalues that are related. Okay, and so if those are both real and distinct, they may not look related because it's two real numbers. Where if it's a complex number, it's actually a complex pair, because they come out as complex conjugates of each other. But if they come out as real numbers and they're distinct, they may not look like they go together, but we can actually put them together to understand some things about this dynamic motion. So for any pair, whether it's complex or real, so I'm just going to say for pairs here, we can compute an undamped natural frequency, and that's just the square root of lambda 1 times lambda 2. So this is called the undamped natural frequency. Okay, and that's the frequency that this system would oscillate at if there were no damping. Okay, now it may not be the actual frequency it's going to oscillate at because it has damping, but we can predict what it would oscillate at if there were no damping. And we can also compute something called a damping ratio. That's minus lambda 1 plus lambda 2 over 2 square roots lambda 1 lambda 2. This is called the damping ratio. And this damping ratio is the ratio of the damping to what damping would be required for it to be critically damped. So if the damping ratio is greater than 1, then this will be an overdamped system. If it's equal to 1, then it's critically damped. And if it's less than 1, then it's underdamped. Okay, a couple more things that I want to point out here are things that we can learn from this sigma, right here. So I'm just going to put this in this box here. So from sigma, we can learn a few things. One of those is what's called a time constant. And that's just 1 over sigma. And that's the time it takes to reduce the amplitude by about 63%. I think the actual number is 62.8, somewhere around there. But basically, the time it takes to reduce this amplitude by about 63%, okay? That's 1 over sigma. We can also calculate the time to half amplitude, and that's equal to minus the natural log of 0.5 over sigma. Or we could compute what's called the 99% damping time. So that's the time it takes to damp out 99% of the signal. So when we are 99% of the way back to our equilibrium, that's equal to minus natural log of 0.01 over sigma. And finally, if our system is not converging, but it's diverging, and that happens if the real portion is positive instead of negative, then our system may actually be diverging and moving away from equilibrium instead of towards equilibrium. So we can compute what's called the doubling time. And that is equal to minus the natural log of 2 over sigma. Okay, so those are some things that we can get from the damping rate. Okay, so hopefully this has been a nice review for you about basic second order differential equations and how we can analyze the eigenvalues that come from that system in order to understand the dynamics of that system.